All right, we have technology. So this is what we're gonna be talking about the theory and the practice. So we'll do the practice first because that will make it more clear what the theory applied to. So you have the transmitter, the receiver, the flight controller, and the ESC, and this goes to motor 1, motor 2, motor 3, motor 4, and then you fly. So you actually have 4 ESCs. This one's a 4-in-1, but that's the same concept. So I'm going to cover what these protocols are in depth for the rest of the lecture, but let's talk about what you're actually going to be doing in the lab. So you're going to have a radio controller. It's going to send radio waves to a radio receiver. That receiver will receive the radio waves. You, as the pilot in command, will be manipulating the controls. You'll be moving those joysticks to fly your drone, and those joystick positions will be converted to a digital signal that'll be sent over the airwaves to the receiver, which will receive that signal. Then it'll interpret that signal, and it will send that signal to the flight controller. The flight controller will then interpret that signal and decide what it sends to the motors, whether it wants motor 1, 2, 3, 4 to be faster, higher RPM or lower RPM. And you're not controlling each motor individually, so there's quite a bit of processing of all of your commands as it goes from your joysticks to the motors. You're just a voting member. You're a voting member in what the motors do, because the flight controller also makes the final decision on what the motors do, and RJU pilot. So the theory of these protocols will be discussed later, but the experiment is you already have the flight controller hopefully finished, and it will have the 0.1-inch DuPont headers. And I don't think I need to explain to you at this point what those are, because you all have intimate experience with them. So they're the pins that stick up. So one pair of 4 will go to this receiver, which you also have in your kit. And that means you need 4 wires from the receiver to the flight controller. Red and black are power and ground. Green and blue in this image are transmit and receive. So you have information going there. In principle, you only need 1 wire. But we're actually later going to want to have information sent back down to the ground later. So here are these 5 controllers. You have plus 5 volts ground, and then you have TX and RX, okay? And so on your flight controller, it actually has labeled there, plus 5 volts ground, TX2, RX2, TX3, RX3, etc. So you're going to pick one of those. And then so this is your goal for this week as far as the wiring. It's actually a pretty easy week. You only have to solder 4 wires once you get the flight controller done. So the radio is the radio master pocket. This is your receiver. So we call this TX and RX for short. And here's the pinout. Now, how do you actually do it? Well, I'll show you in lab how to solder to these 4. It's much easier. But the other end goes into the DuPont headers. So the other end is going to look like this. So what you need to do is go into the lab, get these pre-crimped wires, cut off one end, and they're in the common lab kit, and solder 4 of that end to the flight controller, so it's 4. And then the other end, you slide into these plastic housings, and they have a little diving board on there, and I'll show you in the lab under the microscope. And the pre-crimped metal connector on the end, it's a female connector, but it's got a little hook. So when you slide that into the plastic casing, it grabs the diving board with a hook and you can't pull it out. So you just slide it in and you're done. There's no soldering needed. And then it'll end up looking like this. You'll have 4 robust connectors, and you plug that into your flight controller. So that's the wiring that you have to do for the radio. And then when you're done with the wiring, we need to go back to YouTube to show what it's going to look like. So there's 5 radio tutorial videos. And here's number 5 of 5. So I'm going to mute my own voice. But when your radio is working, you connect your flight controller to Mission Planner, which you should all have, and you go to the Setup tab and the Radio Calibration tab. It'll show you if it's receiving the wiggling of the joysticks. So when you wiggle the joysticks, these should move. It's the throttle, the roll, etc. So once you see that moving, that means the flight controller is receiving the radio signal, and that's your milestone for that week. Okay. Later, we'll figure out how to translate that into flight. Any questions? So the rest of the lecture then is the theory of these protocols and what they all are. Now, I will advise you this lecture will be obsolete soon, the entire lecture, because why reinvent the wheel? You could just use the internet. You could just use Wi-Fi or a cell phone. And that's the way it's probably going to end up going. But what would be one reason not to use a Wi-Fi connection between your drone and your ground control station? Jamming, yeah. What's another?
Lack of Wi-Fi.
What?
Lack of Wi-Fi.
Yeah, no. You can just buy Wi-Fi chips are really cheap. So you can just put one on your drone and one on your radio controller. And probably all of you have what it takes to do that as a senior design project. But why would you not use Wi-Fi as the method of communicating between the drone and the ground? Yes?
Short range.
Range, exactly. So Wi-Fi range is about 100 meters. So, and if you go out to the arc, that'll only get you about halfway across the field. And in fact, DJI did use Wi-Fi for a long time. They used multiple channels, they boosted the power, and so they got maybe a kilometer of range. But its range is one of the main issues not to use Wi-Fi. Jamming and congestion is another. So I think eventually that may be solved. But for now, and historically, pre-Wi-Fi, there were drones, well, there were radio controlled models before Wi-Fi. So we're at a point, we're not quite at the point of inflection where all the transmit and receive protocols that are drone specific are obsolete. And they'll probably never be obsolete because you're never going to get more than 100 or maybe a kilometer with Wi-Fi. So there's that. The other thing that will not, but we're not going to talk about internet control in this lecture. This is all about radio control with drone specific protocols. The other reason that what I'm saying may not be obsolete is we're going to start from fundamental physics and discuss what protocols you could design if you start from scratch and what the trade-offs would be. And to make a long story short, there's a trade-off between range, bandwidth, and bit rate. So most of the lecture is going to be about the theory of that and then how all these protocols fall on that spectrum. So if you want long range, you're not going to have very good bit rate. Question?
Is it not possible to jam a radio wave as well?
It's always possible to jam a radio wave. Any radio wave. Wi-Fi, the other protocols, it's always possible to jam it.
So that's not, that downside is not specific to
No, that downside is not specific to Wi-Fi. And I'm not sure of any general solution to jamming. There are specific solutions, but when you start working with radio communications and jamming, it becomes a technological cat and mouse game. And then it's not because of defense applications. A lot of those games are played behind closed doors, meaning they're classified. So I don't have clearance, so I don't know what all the jamming techniques are and the jamming immune techniques. However, I have a PhD in physics where they invented that quantum bit, and I worked on microwaves and superconducting circuits, and that's where the Nobel Prize came from today. I know physics, and so I can tell you what the laws of physics are and how that frames what is possible and what's not possible. But knowing physics, yes, you can always jam a signal. You just have a really strong transmitter at the same frequency that you're trying to jam, and then it overwhelms your receiver, and then game over. So then you have to hop to a different frequency. But whoever can hop quickly wins. And you can jam all the way around the world. There was a famous case where Cuba was jamming the HF radio waves a while ago. I don't remember what the political reason was, but you can bounce radio waves off the ionosphere and at 7 and 14 megahertz. If you join my ham radio club, we'll do it. If you look at the top of NTSB, I have some big 20-meter antennas, and we send signals bouncing off the ionosphere around the world. And at one point, Cuba was mad at some communication, and they just broadcast megawatts at that band, and they were jamming the entire United States. So yes, you can always jam any radio signal. So that is a disadvantage. Okay. I mean, there are ways around it, but nothing is foolproof. Okay. So so the protocols that we're going to be talking about are the drone specific ones or drone useful ones, including Wi-Fi, but we're going to talk about also the principles that go into this trade-off between range, bandwidth, and bit rate. Okay. And Wi-Fi is kind of the extreme. It's very high bit rate, very high bandwidth, but it's very short range. And the radio controls we're going to be using are the opposite. They're very long range and very low bit rate. And we're going to teach you that through experiential learning, because you're going to have an ESP32, which is Wi-Fi, a Raspberry Pi, which is also Wi-Fi, and you're going to have a long range one on your radio controller, the receiver here, and eventually you're going to connect them both to your computer. And you're going to see that one takes about 2 minutes to download the parameters, and the other one downloads the parameters in about 3 seconds. But you're going to fly your drone across the field at the arc and you're going to see the Wi-Fi connection disconnect, and the other connection will not disconnect. So you're going to experience this trade-off directly. Today is the theory lecture. Why and what are the quantitative equations? And today's also the lecture about all the different protocols, so you know what the latest and greatest is as of this moment. Okay, so there's the radio. Just as a background, we have yaw, pitch, and roll. So the pilot inputs in those 3 dimensions are going to determine whether the drone tilts to the right or left, forward or back, or rotates. That's yaw, pitch, and roll. And then this one is throttle, which is, if you give it a lot of throttle, it's going to go up. If you give it not any throttle, it's going to fall like a rock. So that's throttle. So you have 4 controls. And you can have as many as you want. It's only limited by money and bandwidth and computational power. So I bought the cheapest radio I could find for this purpose. That's why I picked it. Not because it's the best, although it's pretty darn good. But I think we have switch 1, switch 2. Those are 2 position switches. They're 3 position switches. You can use those. And then, yeah, so you have 6 channels that you can send up and down, and you can use them for what you want. We're going to use one of them for arm disarm, and the other one's going to be used for flight mode. So that's the 6 channels. I should say practically that these little joysticks here are what's called trim. And that means it'll, instead of sending a neutral signal, it might always send a little bit pitch forward, or always send a little bit pitch back. So make sure those trims are set to 0 when you're flying, or your drone will always be tilting to the right, or so on. And you can see where the trim is set by this little black symbol here on this slider. There's one here, there's one here, there's one here, one here. And then there's an LCD. So like everything, there's a microcontroller in there. There's an STM32 microcontroller in there. And it's running this code, which is showing you on the LCD some information and allowing you to interact with the microcontroller and the drone. So there's also these buttons here that allows you, it's like a user interface to get at what the program is doing. Oh, you can't see the screen, can you? Can you see it? I can't see it from here. Yeah, so there's an LCD on here. Sorry, it looks okay on my laptop. But let's just move on. Okay, you'll see that in the lab. So there's an LCD there that gives you information, and these buttons program it. You can play Tetris on there. Raise your hand if you know what Tetris is. Everybody knows what Tetris is. Okay, so you can play Tetris on there. So it's a decent little tiny microcontroller with some RAM and that you can run code on. And by the way, we're going to be downloading all the code. We're starting from scratch. So out of the box, it probably will work. And you're going to have to tweak the configurations. But the Peter Burke philosophy for this class is we're doing it all from scratch. So you're going to wipe all the code from all of everything you have and start from scratch. So that's why there's 5 YouTube videos. And it's important to have that skill for many, many reasons. For the drones in particular, it's important because there might be a new version of the firmware that comes out, and it might add some extra functionality. And you need to know how to install the firmware. Okay. And also, when I buy the radios, I have no way of guaranteeing what version of the firmware is on. So if I bought 43 radios for you, you bought them with your lab fees, and there's no guarantee what version of the firmware is. And it could be that, so I don't have time to have 43 different firmware versions and troubleshoot them all. So we're all using one firmware. Okay, this is the receiver. Actually, it's a beautiful little device. It has an ESP32 microcontroller on it, which has its own built-in Wi-Fi. So it's got a little Wi-Fi chip here. And so it's one side is a microcontroller, which is basically an Arduino. And it's going to run the receiver code, which will download. The other side has the long range antenna. So the protocol figures of merit for all these protocols. Now we're going to go through each protocol one by one and talk about the trade-offs, the engineering trade-offs, and what the quantitative relationships are between the engineering trade-offs. And we're going to go deep into radio wave electromagnetics, which is covered in 180A. Raise your hand if you took 180A. Okay, it's going to go deep into signal processing, 241, I think. Raise your hand if you took 241. Or no, you took a signal processing course, right? Communications? Yeah. It's 141, right?
You're talking about DSP?
Yeah, it's one of them. There's several.
There's the 2A.
And have they taught you Shannon's information capacity theorem?
I think we covered.
Okay, so we're going to do it again today, and you're going to get visceral hands-on experience. So we're going to go through all that theory as it applies to radio control in general, drones in specific. So range is one. Let's say you're a drone pilot. What do you really care about? Range is one. Number of channels is another. So ours is 6 channel. Latency is another one. So racing pilots like to have less than 20 milliseconds of latency because the human response time is something like 20 milliseconds. And so if they have 50 milliseconds of latency versus 20 milliseconds of latency, and they're doing drone racing, they can tell. So they really worry about that. Me personally, I'm not a drone racer, and neither are you in my class, so you don't care. But that is a trade-off. And then telemetry means two-way flow of information. Okay. So here are the TX protocols that are on the market. TX protocols meaning this, the protocol for the radio wave. So you all know about smoke signals. You all probably know what Morse code is. Morse code is, dashes and dots. So if the radio wave is on for a long time, it's a dash. If the radio wave is on for a short time, it's a dot. And then the rest of it is communication theory, which the class is, there's a communication theory class, right? Which one is, I have it listed. I don't teach it, so I forgot the number. It's 160 something. So going from Morse code to 1000-bit quadrature amplitude modulation, which is in Wi-Fi, that's a whole class. But that's the lower end protocol of how you get the bits. But once you get the bits from A to B, how do you interpret those bits? So that's the transmit protocol that are available to you as a drone pilot. They're listed here. And some of them are open and some of them are proprietary. So we can't go through all of them. I'm just going to go through the common families. This is the spectrum. And it's proprietary. And most of these are 2.4 gigahertz unlicensed band. Or some of them are 5.8. So you can broadcast on 2.4 or 5.8 without a license from the FCC. Bless you. So that's why they use those bands. is you don't need a license. If you want to broadcast cast at 1.9 gigahertz or let's say 126.8 megahertz, you need a license. Anybody know what 126.8 megahertz is? It's a John Wayne Tower air traffic control frequency. Do not broadcast on that frequency. Okay, and you need a license. So, but 2.2, 2.4, 5.8, those are open. So, Spectrum uses them, and it's proprietary, it's low latency, and it's well funded because it's the hobbyists and the racers. So that's still in existence. These other ones, they're cheaper, and they're, I would say, fading out. I mean, they're still in use, but they're being replaced by ELRS de facto. So those were around initially, and they were okay, but they were fine actually. I think Futaba might be out of business, I'm not sure. But there's always competing protocols, and Spectrum is the most expensive and the highest performance, lowest latency protocol that's still around. So in the range of these protocols was really typically about, let's say, 500 meters, okay? So they were meant for short range flight. Now, the newer protocols that came online are Dragon Link, which is ultra long range, 1 to 100 kilometers. I think that's proprietary. And it was a small company in Eastern Europe that invented it. And kudos to them, and you could control a plane from 100 kilometers away. So that was the first generation of long range control. The most recent ones are these two called TBS and ELRS. TBS stands for Team Black Sheep, is the name of the company. Crossfire is the name of the protocol. And the underlying RF protocol is LoRa. So it's similar to Wi-Fi. LoRa is a similar standard to Wi-Fi. So they take the LoRa protocol for the bit communication, and they add on top of that their Crossfire interpretation for the radio control. So LoRa is sort of the low level bits in RF, and then Crossfire is the high level the code. What do the bits mean? Do the bits mean go left, right, up, down, whatever, okay? And Crossfire was proprietary, but now it's been reverse engineered and turned into ELRS. So it's kind of like Linux now. You had Unix, which was proprietary. I don't know the history. Some of them were open, some were proprietary, but then you had Linux, it's all open source. So ELRS is like the Linux of radio control, and LoRa is a closed source RF protocol like Wi-Fi, but it's very long range. So this is what we're using, ELRS LoRa RF. I wonder if we should skip the theory and go right to what they are briefly. Okay, let's talk about, well, look, no, we need to do some theory. So before I go further, the goal of the next 15 minutes maybe is to explain the antenna theory and bandwidth and signal to noise trade-off, okay? So put your thinking caps on. There might even be some equations, and you're going to come out at the other end with a complete understanding at a high level of hardware, software, communication systems. So this is the formula we want: transmit, receive antenna for signal. We'll do about noise and bit rate later. And this is the log version. It's called the free transmission formula. So I have 3 handwritten slides that I'm going to put onto the thing here to explain to you that formula so you understand it. And it's pretty simple, actually. Consider the sun. The sun is emitting light in all directions. Now consider a sphere at a distance r away from the sun. First of all, how much power is the sun emitting? The sun is P sun is 10 to the 26th watts. That's 10 to the 26th joules of energy per second that are emitted by the sun out into the solar system. And it's emitted the same in all directions. Now, consider an observer at a distance r away. What is the area of that sphere distance r away? A sphere of radius r, what's the area? 4 pi r squared. Okay, that's the area of the sphere. So we can calculate, if you're at the Earth, surface of the Earth, the power density, which is defined as the power per unit area at the surface of the Earth. So that's going to be 10 to the, that's going to be P sun over 4 pi r squared. That's the power density at the surface of the Earth. And we can do the math on that. If the Earth is 10 to the 11 meters roughly, you can do the math. And in the interest of time, I'll save you. It's about 10 to the third watts per meter squared. So if you have a 1 meter squared solar panel with perfect efficiency, you can get 10 to the third watts of energy out of the sun. In reality, they're only like 10%. So you might get 100 watts out of a 1 meter squared solar panel. So, okay, that's that. Now, Professor Burke, how does that relate to antennas? Well, that's page 2. Radio. So consider a transmit antenna. I'm going to draw it like this. That's transmitting radio waves. Okay, and let's assume it's transmitting radio waves in all directions. You've all seen antennas, you know antennas. But for the moment, let's just assume it's a omnidirectional antenna. That means it transmits in all directions. So the antenna is sending radio waves out, and you consider a distance r away, and we have PTX is the antenna. Here, the power density is PTX over 4 pi r squared. That's the power density of the radio waves. Okay, so same thing as the sun, because they're both waves, and they both propagate through the universe according to the same fundamental laws of physics, Maxwell's equations. If you take 180A, you learn all of Maxwell's equations. If you don't, this is all you need to know for this class. Now, the only trick is the distance is usually large compared to the wavelength, because the wavelength at 1 gigahertz is 30 centimeters. So usually distance is many, many, many times 30 centimeters. But your receive antenna, that's a little more unclear what that needs to be. So I'm going to tell you there's a theorem. So let's say you have a receive antenna, RX, and it's an antenna with 2 wires. If it were an omnidirectional antenna, then the area of the antenna, so the total power received is going to be the power density, so P transmit divided by 4 pi r squared, times the antenna effective area. AFF is the effective area of the antenna. Okay, so what is that? Well, there's an antenna theorem that says A effective is equal to lambda squared over 4 pi. So the effective area of an antenna is approximately the wavelength squared, if it's omnidirectional. Now, if you take Filippo's antenna class, they might go through that. Is anyone taking Professor Filippo Capolino's antenna class? You are? Have they done this yet? Effective area?
No.
Have they done free transmission formula yet? Okay, well, they will. This is his entire class in 5 minutes. Okay, so yeah. So, but you gotta, we have places to go and people to see. Okay, we want to fly our drone and we want to use antennas to do it. So that's what I'm going to give you the basics. So the effective area of an omnidirectional antenna is lambda squared. So we can work out the receive power is the transmit power. Oh, I forgot the square there, by the way, 4 pi r squared. And then the effective area of the antenna is lambda squared over 4 pi. So now we have the free transmission formula, which is that the ratio of the received power to the transmitted power is lambda over 4 pi r squared. So that's the free transmission formula. And I'll divide it into colors. I'll circle it in color because it's so important. So before we go any further, let's just stop and think. First of all, the power that you receive goes as 1 over r squared. The further r you away, the lower the power. Now, if there was no noise in the universe, it wouldn't matter because you could receive a tiny power and just amplify it up. And you all built amplifiers, right? Well, some of you, the EE side has. In 178, we build amplifiers. So you can always buy an amplifier from Amazon or whatever, or contact your electrical engineering friends and have them design and build one for you, and it'll amplify up that tiny signal that you receive at 1 gigahertz or 2 gigahertz. And if the amplifier had no noise, then it wouldn't matter if the signal had decayed. So noise matters. There's always noise. So the first half of this segment is about signal, then we'll do noise, and then signal to noise. So the signal drops as 1 over r squared. So the further away you are, the worse, the lower the power. And then the other is that you have this ratio. Once you have the antenna in place, the ratio of received to transmitted power is independent of things if they don't change. So the only way to get more power is to boost the transmit power. So in principle, you can boost the transmit power up to infinity and solve that. But in practice, that's not possible. And the FCC typically limits us to between 10 milliwatts to 1 watt. Because if we broadcast at a megawatt, first of all, where are you going to get a megawatt? You have to have a power plant to get a megawatt. So let's say you buy a power plant and you put a megawatt into your antenna and you transmit. That's going to interfere with all the other Wi-Fi around. So they limit it so that it's fair. And not to mention, you don't have a megawatt power source on your drone. So, and ideally you want that as low as possible for battery. So that means that PRX is limited to PTX is limited to 1 watt. So PRX is going to be pretty small. And actually there's an app on your phone called, for Wi-Fi, called, if you have Android, called Wi-Fi Analyzer. Does anybody have it?
What's it called?
Wi-Fi Analyzer. It's only for Android. And it'll show you all the, nobody has Wi-Fi Analyzer? Well, get it. And if you have Android, it'll show you all the Wi-Fi channels that it's receiving. It'll show you the power level in dBm. So you can do an experiment, you can walk away and you can see that it falls to 1 over r squared. So this is the power level. And this blue one, UCI Wi-Fi, is minus 50 dBm. So I'll do the math for you. 0 dBm is defined as 0 dB relative to a milliwatt. So you don't need to know dBs for this class, but if you know dBs, you'll get it quickly. If not, don't worry, I'll convert it. So 0 dBm is 1 milliwatt. And remember, our transmit power is 10 milliwatts. Typically, Wi-Fi is 100 milliwatts. So that one right there is probably putting out 100 milliwatts. So I'm getting minus 50 dBm, which is 10 to the minus 5 of milliwatt, which is 10 to the minus 8 watts. So on Professor Burke phone, because I have the app, I have 10 to the minus 8 watts of Wi-Fi signal. Okay, so it's 100 milliwatts up there. It's 10 to the minus 8 watts on my phone. And I have some other ones that go down to minus 90 dBm. So that's 10 to the minus 12 watts. So it's pretty amazing that your phone can pick up 10 to the minus 12 watts reliably. And that's modern technology for you because they amplify it like crazy. But at some point you get to the noise level, which we'll talk about later. So Your drone has a similar set of numbers where you might start out with 10 milliwatts, but you're going to end up getting a nanowatt, 10⁻⁹ or picowatt, 10⁻12 at the receiver. Okay, so that is this formula right here called it's called the free transmission formula. It's a famous formula. The only exception to that formula is that we assume that antennas are omnidirectional. And that's page 3 of the lecture, 3-page lecture. So the antennas are not omnidirectional, okay? So if you make an antenna out of wires and it is illuminated with a radio wave, the effective area, it's more sensitive in one direction than the other, okay? So there's a directivity to the antenna, which they call gain. So the effective area, I guess the best way to say it is that the effective area of the antenna is lambda squared over 4 pi times some function of theta and phi, okay? And that's the radiation pattern. So the function of theta and phi depends on the direction that the waves are coming in from, or that the waves are going out to. So it can be, it's got to, theta and phi, it's got to be greater than 0, greater than or equal to 0. So there are some directions where you will receive no signal from the antenna. And it's got to be less than or equal to infinity. There are some directions where you're really, really, really sensitive. And these are mathematical. These are mathematical. So the antenna pattern is the direction. You might have something that looks like that for a dipole. So the radius is how sensitive it is. And raise your hand if you've ever heard of the Bermuda Triangle. What happens in the Bermuda Triangle? Ships get lost. What else gets lost? Planes. Now, Peter Burke has a theory. Part of the reason for that is the plane is flying and the radar has a 0 where the plane angle is. So the plane flies into the null of the antenna and then flies back out again. So it literally disappears from the radar, even though it's still physically there. So the reason I believe that theory is that some antennas are not sensitive in certain directions. Okay, so what do we do about that? Well, we use them in the most sensitive direction. We never use an antenna in the least sensitive direction. And so if we use it in the most sensitive direction, then this quantity might be greater than 1. So what we say is that at the maximum theta and phi, it's called the gain of the antenna, which could be the receive antenna, G sub r, okay? So G sub r is a number that's greater than 0 and less than infinity. And that's how much more signal we get because we're pointing in the right direction. And the same thing for the transmit antenna. Maxwell's equations are symmetric. So the effective free formula has the gain of the transmit and the receive antenna in it. So if they're misaligned, you're going to get no signal. That's what happens, in my opinion, to some of the planes that so-called disappeared in the Bermuda Triangle. And if they're aligned, you're going to get more signal than you would have if it was just an omnidirectional antenna. Instead of lambda squared, you get this enhancement. So that's the free formula. And then in practice, we need to go through some antennas, but in practice, you can get 10 to 20 dB of gain typical. You're not going to typically get much more. That's log, linear. It's this is 10x more effective area. This is 100x more effective area, okay? So by using the right orientation with the directional antenna, you can get more effective area. So let's do an example antenna. The simplest one is a dipole. And this is from Professor Filippo Capolino antenna course, okay? I'm only going to give you, I think, 2 example antennas, unless you ask, but let's do 2. So here's a coax. Now we take the center pin and we bring a wire up, we bring the ground pin down, and that length is lambda over 2. So it's called a dipole antenna. And so if it's a 1 GHz antenna at 30 centimeters wavelength, the actual antenna length is 15 centimeters, so each arm is 7.5 centimeters. So that's fine. And what happens there is that it's got a gain of 1.64 dB. That means it's directional, but in the best sensitive direction, you're only getting 1.6 dB more than you would with an omnidirectional antenna. So you really don't get much, okay, with a dipole antenna. It's just easy to make and easy to understand and easy to use. So, I mean, come on, it's 2 wires. So in my 280 class, we actually make some with 2 wires. And actually, my TA, you're taking Filippo Capolino's class? So my student is your TA, and I'm gonna have her help make some antennas for you and measure. But just with wires, actually, I made them in my garage, but it's pretty simple to understand. However, there's one problem, which is the directionality. So it's least sensitive where the antenna is pointing. In fact, it's a null in the direction perpendicular or parallel to it. So there's 0 radiation in this direction. So if you point the antenna at something, it's a mathematical no. You get mathematically nothing. So that would be a Bermuda Triangle type experiment. And the reason I know is that, well, I'm a teacher, but when I was young, before I learned all this, we had these 50 megahertz radio control signals because there was no 2 gigahertz silicon transistors back there. Moore's law, the gate lengths were still hundreds of microns. The cutoff frequencies were 100 megahertz. So we had to live on the 50 megahertz band, and we had to have a big antenna, and it stuck up out of the controller, and I used to point the antenna at the airplane to try to get better signal. That's the exact opposite of what you should do. It seems like you're pointing the wire at the radio at this where you want it to go, but that's exactly where it doesn't go mathematically. Want to know why? Take Professor Capolino's class. But it will go like a donut around it azimuthally. So the radiation will be broadcast perpendicular to the wire in any of the directions. Parallel in the parallel direction, you get nothing. And receive and transmit are the same. Okay, so that's one example antenna. And you're going to have you have a dipole antenna. I believe this is a dipole antenna right here. Okay, so don't point that pointy end at your drone because that's a minimum. You're going to have a dipole antenna on your FPV camera, your little camera. It's got a tiny little antenna, and it's on the drone. So here's your drone, and here's your camera, and here's your dipole antenna. So it needs to be, and so you need to orient that vertically. If you have it horizontally on the drone, which I see a lot of drone pilots do, and they don't understand what I'm about to teach you. Let's say this is the antenna, the pencil is the antenna. I put it on my drone. Now you're going to get good signal, right? But let's say the drone rotates, and you're the drone pilot. You're not going to get good signal if it's pointing at you. So most of what the drone does is rotates. So don't mount it horizontally. I see so many drone pilots do it horizontally, and I cringe. So now there's one exception, which is when it's over you, but it's almost never exactly over you. The other thing is, so I would orient it vertically so that when the drone flies around, you're always getting the maximum signal. The only time you won't is when it's right over you, you get a mathematical null. And if it's right over you, you're not long range away. You don't care that much around range. And it's not it's not zero, it's mathematically zero, but there's still some finite transmission. We always want to have a big buffer. So, and if it gets fail-safe right over you, then it'll just land through fail-safe. So have it horizontal, have it like this so that when it's far away. Now, if you're racing and going back and forth, it only depends on the sine squared of the angle, so it really doesn't matter that much. If you're racing and your drone tilts and happens to point at you, so it tilts 90 degrees, yeah, then you're gonna get a null. So if you're a drone racing pilot and you like to do flips and rolls, then don't use a dipole antenna. And the drone racing pilots don't. They use something called a clover leaf, which is more close to omnidirectional, but I told you I'm gonna give you one antenna, so dipole's one. And then the other one is a Yagi, which is very directional. You can have 10 to 20 dB of directionality, and that one you've all seen on the roofs of buildings, okay? And you've all seen that, right? Has anyone not seen an antenna that looks like that? Because I can show you pictures if you want. Okay, so it's from the old fashioned, well, let's do it just in case. I mean, and so I have one on the roof of MTSB, which you can see. It's a 20-meter Yagi. It's only 3 elements, but it's designed to be directional. And what's your name taking, Professor Capelino?
Eduardo.
Eduardo, you're the antenna czar for the class. When Professor Capelino talks about a Yagi, you tell us, okay?
He went over it briefly, just the introduction.
Okay.
That and why that.
Okay, well, so you're gonna do a whole quarter. So Yagi antenna is very directional. It looks like that. This one's really directional because it's got a lot of elements. The more elements you have, the more directivity you have. So this one has a lot of elements, so it's very, very directional. Mine on the MTSB roof has only 3 elements, so I think it's about 10 dB directivity, but you can get 20 dB directivity with a better one. So if you want to send a signal to the moon, then you need to tune your Yagi so that it's pointing at the moon. And then you'll get 20 dB more signal than you would if you had an omnidirectional antenna. But if you point the Yagi away, you're not going to get anything at all mathematically. So that's the signal part, and then we need to continue. So if you have 2 dipoles that are pointing at each other, you're getting a mathematical null. Even if one's pointing at it, it's getting a mathematical null. So they need to be parallel to get the maximum signal. Okay, now let's go back to this formula just for fun. And because I am going to do a little bit of math and dB. So dB is useful. It's defined as the 10 times the log of P1 over P2. So it's a relative power measurement. So instead of saying the ratio of power P1 and P2 is something, you take 10 times the log of it. That's the definition of decibel. Those triple lines mean definition. Okay, so the reason people in engineering like to use dB is this right identity at log A times B is log of A plus log of B. So if you have 2 quantities in engineering that multiply, like the gain, and you want to separate them out easily, you take the log of both sides, and then you end up with the gains and losses are adding if you're using decibels instead of multiplying if you're using linear units. And it's easier to add than multiply. That's simple. It's undergrad, it's like elementary, bless you, kindergarten math. So the interesting thing about it is the free space loss. And we're going to talk about this when we do GPS, but for GPS, the wavelength is 30 centimeters. The distance is from here to the GPS satellite. So this is like 100 dB. Or in linear units, that's 10 to the 10. So that means the power you receive at Earth compared to the power transmitted at the GPS satellite is down by 10 orders of magnitude. So free space loss can be very important. It still works though. So it's really amazing because you amplify it. So that brings us to noise. Noise is always present in any system. So let's say you have a TX antenna, you broadcast your signal, you have an RX antenna, you receive it. Let's say this is 1 watt, let's say it's 10 minus 12 watts. Now you want to amplify that up with a high gain amplifier. And now the signal maybe can be 1 milliwatt again, and it can go into your CPU and you can process it. So if there were no noise, that would be fine. You could just turn the gain up, or we can just add as many amplifiers as we want to get the gain, but there's always noise. There's amplifier noise. So you hire the best RF engineering team that you can, and you get the amplifier noise down as low as you can. But there's also environmental noise. And that is, and that's the same thing, it's equivalent to black body radiation. So here's a physics factoid for you. Any object, well, let's start with the sun. The sun is really hot, it glows yellow. If you light a fire when you're camping and the wood gets really hot, what happens to it? What color does it turn? Red, and then white. So the red is it's emitting red light, and you feel that on your face as heat. But before it gets quite that hot, you still feel the heat on your face, right? So it's in the infrared, you can't see it. So it turns out that any object will emit radiation that's at finding temperature at all frequencies, including microwave frequencies. At microwave frequencies, there's not much, but there is some. So if your amplifier is perfect, there's still always some background noise, no matter what. And that is a fundamental limit of the laws of physics. The only way to get around it is to cool the Earth down to 0 degrees Kelvin. Short of that, there's always noise. So noise is inevitable in finite temperature systems according to the laws of physics. So we have signal, we have noise. So that brings us to the Shannon information capacity theorem. So what matters isn't the signal, it's the signal to noise. So the signal's dropping as 1 over r squared. Signal's proportional 1 over r squared. The noise is pretty much fixed. There's not much you can do about it because it's the finite temperature of the object that you're looking at. Yeah, it might change a little. And actually, that's how infrared vision works. So night vision, where you use infrared goggles, you're looking at the infrared portion of the spectrum at the thermal radiation emitted by that body. So that's why warm objects appear a slightly different intensity than cool objects. They're both emitting, but you can make an image out of the different emission power. It's tiny, tiny, tiny power. So that's why infrared cameras are still very expensive, because we don't have very good, very sensitive detectors. That's a class for semiconductors. Okay, that's a semiconductor class. But the signal is going as 1 over r squared. The noise is fixed. So Shan, and then B is the bandwidth, which is how wide your signal is. So you can broadcast at 1 gigahertz plus or minus 1 hertz, or you can broadcast at 1 megahertz plus or minus 10 megahertz. And if you take a signal processing class, they'll tell you all the different ways of modulating the signal. We'll do a simple example. AM means the RF power is on for a while, and then it's off for a while, and it's on for a while, it's off for a while. So this is the RF. So if you take the Fourier transform of that, the power versus frequency, this is the carrier frequency, F naught, and it's the spread out of the bandwidth here, in this case, is equal to the AM bit rate for AM. But there are other modulation techniques that you can use, okay? So the more bandwidth you have, the more bits per second you can get. And what Shannon's information capacity theorem tells you is that the available capacity of a channel in bits per second is equal to the bandwidth. So the more the bandwidth, the more the bits per second, times the log of 1 plus the signal to noise. That's the Shannon information capacity theorem. So that gives us our trade-off between, that's the quantitative equation, that's the trade-off between range, which is again signal, bit rate, which is Shannon's capacity, and bandwidth. So this is the equation that describes them. So which do you want? Do you want long range or do you want high bit rate? You can't have your cake and eat it too. That's what Shannon's theorem says. That's a fundamental, profound theorem from statistical properties of communication channels. He should have got the Nobel Prize for that, because we use it all the time in our daily life. Okay, so that's the theory. So what does that mean for me? Well, the rest of it is just math. So if we take Wi-Fi, we can go through the numbers, and we typically use a bandwidth of about 10 megahertz. And we typically, now these are approximate, we have a bit rate of 100 megabits per second, and we might have 100 milliwatts transmit power because that's FCC limited. So that's what gives our range of 100 meters. That Shannon equation gives us our range of 100 meters. So the only thing we can do to get longer range is to make a bigger bandwidth or bigger power or lower bit rate. Now, to make the power bigger, like I said, will cause interference. To make the bandwidth bigger, well, you can do that. So Wi-Fi initially started out as 20 megahertz, and then they started doing 40 megahertz channels. And you can actually stitch channels together and use a lot of them at the same time to get much larger effective bandwidth. But at some point, you get to the range where you're between, I don't know what exactly, 2.1 and 2.4. If you go beyond that, above or below it, you can start interfering with police radios and air traffic control and all sorts of stuff. So bandwidth is a precious finite resource that's literally worth billions and billions of dollars. And whenever a new technology comes along, industry competes fiercely in the political and the economic region to buy the bandwidth. And now it's Starlink. In your career, in your life, there'll be some other Starlink 2.0 and some other Elon Musk will die, another one will be born, and he'll have a new version, and they're all going to be competing because they can't change the laws of physics. The bandwidth is set by nature. So typically auctions, when they come up, the companies spend billions of dollars for the right to use the bandwidth. Okay, so that's the bandwidth. So that's kind of set. So the other one is bit rate. So our radio controllers have a low bit rate, okay? And they have a low bandwidth and a low power, and they get much larger range. Because for a radio controller, we don't need 100 megabits per second. It turns out for video, like YouTube quality, you need about 20 megabits per second. Anything less than that, you get degraded video quality. But if you're only sending the position of 4 control sticks at 1 kilohertz, you can do the math. You're encoding the control stick at, let's say, 1 byte, so 1024 different levels, and you're broadcasting that at 1 kilohertz. So you maybe only need a megabit per second or 100 kilobits per second. And this also goes to latency. So if you want super low latency, you have to have a high bit rate. But if you had a bit rate of 1 bit per second, then you could have a very long range. In fact, if you want in ham radio, I'll give you one more example. Ham radio, it's called FT8. It's another thing, and every 30 seconds they get, I think, 100 bits. So it's so that's about, let's say it's 30 bits, so they get about 1 bit per second, and that's FT8. So that's the complete opposite. And just for fun, if you join my ham radio club, you can do it. And I have on my roof a receiver that receives FT8. And this is my call sign. And this is everything I've sent and received in the last 24 hours. Uh-oh. Let's see. How's that possible? Okay, well, I guess my system is down, but we can say, instead of the call sign me, we could say anyone. So people report what they get. So you can send signals around the world because it's very low bit rate. You can go all the way around the world. So that's FT8. In fact, if you take ham radio, it's a great way to learn because, bless you, these are all the digital modes that ham radio people use, okay? So they're all digital modes. So there's lots of digital modes, but they all follow this fundamental Shannon information equation. Okay, so let's now get back to drones and so this is not a ham radio class, this is not a Wi-Fi class, it's a drone class. So you could reinvent the wheel, which they did up until Express LRS, but Wi-Fi is a standard that has high bandwidth, short range. Cellular is high bandwidth, longer range. And so the industry got together and said, well, what about all the Peter Burke and QV Dang students that they're senior design projects. They don't need really a lot of data. They just want to measure the temperature once a second and have it wirelessly read out. Well, the industry got together and said, let's create a new standard, and they did. It's called LoRa. I think that means long range something. So that's an industry standard similar to Wi-Fi, and we're using that for our drones. But you can also use it for your senior design projects. Is anybody using LoRa? Okay, you're doing everything. Two, so, well, you're all going to use it by the end of the quarter because you're taking my class. So it's part of the Express LRS. Oh, I guess now we need to go a little bit back to the Express LRS. And actually, let's so Express LRS is the Linux of it. It's open source. No, Express. Actually, they're in the middle of a big fight now. But it's the radio control protocol. But let's look at your Happy model 2.4 gigahertz RX. This is the one you have. So this top of your receiver, the bottom of it is an ESP32. The top, it has a crystal. This is the antenna, the receive antenna for your radio signal. It's pretty nice. It's compact. And then you can see it's looped around. Ask Filippo to explain that to you. But this is the LoRa chip. So it's a LoRa chip that uses LoRa protocol. So on one side, it receives a LoRa signal, and then it sends it to the ESP32 on the other side, and then that turns it to a digital signal, which sends to your flight controller. So that's what ESP32 uses in LoRa. And that's why they can get range of hundreds of kilometers. All right, so it's 137. We have one more thing to discuss, a couple more, which is the receiver to flight controller protocol. Short answer for you is going to be UART. Oh, I do have Express LRS here, but let's do the medium answer. There are quite a few receiver protocols. Let me do just the beginning and the end. So PWM is pretty simple. You saw PWM, right? That's the pulse width modulation, where all you're doing is taking the width of a pulse that comes 50 times a second. It's either 1 millisecond width or 2 millisecond widths or anything in between. So that's pulse width modulation. And what PWM does is it takes the radio signal and it converts it for each channel. This is an 8-channel receiver into a PWM signal out. So this is like stick and rudder flying. If you push the stick to the right, the PWM signal coming out of 1 changes. If you push the stick down, the PWM coming out of pin 2 changes. So there's no autonomy, there's no intelligence, there's no programming. It's just direct PWM out, which is directly controlled by your joystick. Okay, so that's called stick and rudder flying, because as a pilot, you have full control of the control surfaces. And that's Boeing's philosophy. They always want the pilot to have direct physical link between the controller and the motion of the control surfaces on the wing. Now, Airbus philosophy is the opposite. They have a joystick that goes into a computer, the computer interprets the joystick, and that goes to control the surfaces. So PWM is not very good because that's big. You don't want eight wires going to your flight controller. You guys have already soldered enough this year, okay? So how can we make it less? So one way is we can serialize it, so we can put the PWM on H1, but that's still an analog signal. So it'd be better to make it a digital signal. So S-Bus is a digital signal, but Crossfire is the digital signal we're going to use, which is the same as ELRS. So that's the one we're going to use. In Crossfire, I don't even have it on here. It's the ELRS signal, and it goes right into your flight controller. And all you need is 1 wire, transmit. Actually, 2 wires, transmit and receive. So the physical is a UART, and the protocol is Crossfire, CRS XF. And that's the parameter file you set in Mission Planner. Now this one is for internet. We'll do that later, okay? So later in the course, we're gonna fly our drones over the internet and we're gonna use Mavlink. In the interest of time, we'll skip that today. So here's the S-Bus protocol, which we don't even care about anymore. Here's the DSM transmitter. Here's TBS Crossfire. product line. It's called Team Black Sheep. Great company, founded by an entrepreneur named Trappy. And he did a great job starting this company and taking LoRa and bringing it to the radio control market. But ELRS now has reverse engineered it and made an open source version of it. So because it's open source, you can buy ELRS transmit and receive hardware from many companies. We're buying one from a company called Happy Model, but there's lots of companies. If you go to Amazon and type in ELRS, Express LRS, you have all these different products, receivers, transmitters. You can even integrate them on the flight controller. And they're all cheap. You look at the prices here, it's $20 for a receiver. And small. It's 1 gram. Your ELRS receiver is 1 gram, and it can get 10 kilometers of range. So here's another list of all the protocols. And now this is your flight controller. So you've soldered all these, and you can connect your radio to these UARTs here. You have TX2, RX2, TX1, RX1, TX5, RX5, TX4, RX4. And if there was any fairness in the universe, you could use all of them, but the universe is not fair. So you can only use TX2 and RX2. And the reason is it can actually do all these protocols, and for some reason you have to hardwire the microcontroller to use all those protocols with all the timers and demodulators and modulators. So for our flight controller, we can only use TX2 and RX2 for our radio controller. That's the bad news. The good news is you can pick any radio you want. You can pick any protocol, S-Bus, SLRX, iBus, DSM, Crossfire. You can pick any of them. I pick Crossfire for you, but if you want, you can go buy a radio that's a different protocol. You can plug it in. You have to tell Mission Planner, or sometimes it'll auto detect. And then the other bad news is that it says RX2 on the board, but in Mission Planner, it's called Serial 6. And that's another thing. I don't want to get into that rabbit hole, but there's some mapping from the label, the physical label on the board, to the virtual port inside. If you use my parameter file, it'll work. But if you want to know the details, here's a link to the web page. Now let's talk about in practice radio. So ours is what's called an all-in-one. But let's say you're a drone pilot, you get hooked on it after you take my class, and you have all sorts of drones in your garage and all sorts of different protocols. Do you have a radio for each drone? No. So you can use one protocol for all the drones and have one radio, but you might have different drones or planes that have different protocols. So instead of having a different radio for each protocol, you can have just the radio with no actual radio. It's just the sticks. There's no waves being transmitted out, and then you put a module in the back called a JR style module, and that has the radio transmitter on it. So typically, if you buy a radio controller, it'll have an internal radio, but you can also plug in the external one and use the external one. You can swap them out. So you can swap out modules. So you can use Express LRS, you can use Dragon Link, you can use DSM, you can use A, B, C, D protocol, and just swap the module out. We don't do that. So we don't do that because I'm a cheapskate. I want to get all of you guys experience. Okay, in the material science engineering, great department, great program. UAV Forge, they win all sorts of national competitions, but it's 50 students in one drone. So my philosophy is the opposite. It's 3 or 4. So I'm trying to keep the cost down. But so ours is the radios inside. Okay, but there's lots of them you can buy. Now, the other thing to know is that, so you have firmware for the receiver, there's firmware for the transmitter, which is Express LRS, and then there's firmware for the user interface. The user interface is called EdgeTX. And EdgeTX, you can play Tetris, you can get color screens, you can even get an artificial horizon for your drone on there. You can get a map on there, a low resolution map, and plot where your drone is on GPS. So Express LRS is the operating system of the radio controller minus the radio part. It's the sticks and the interface. So you're going to flash that also. Those are EdgeTX compatible radios. You get a lot of flashing to do. Now there's one more, other than the internet. So the internet is eventually going to replace all this. We'll do that in the second half of the course. But it didn't work until December of 2024. So up to December 2024, it was all these protocols, and it's still most of these protocols. but I'm gonna bring you up to speed. And the internet's not perfect either, because you gotta have an internet connection. But there's one more elephant in the room, which is DJI. So DJI has the lion's share market of drones. They have their own, everything's proprietary. It's kind of like Apple. RGPile is like Linux, it's all open. And DJI is like Apple, it's all closed, but it just works out of the box. So most of them are drone and controller systems, and they have their own video, everything. But they do have the option to have a radio controller and a link piggyback on their video signal. And so that is another option for remote control with DJI. It's proprietary. They have about a 10-kilometer range, so you can have video and radio on there. And it's better, but it's like $500 for that whole set there. That's just the camera, the radio, and the goggles. So because we don't have the budget, we're going with the $10 receiver and the $70 transmitter. But if you want to spend $500, you can buy this, you can put it on your drone, it'll work. Just as good for the radio, better for the video. They're not quite compatible. It's kind of like getting Linux and Apple to work together. So you're not going to get Mission Planner integrated with it. So the reason is DJI is closed source, but that is another option for radio control. Okay, so that's the state of the art of radio control. On Friday, you'll start putting together once you get the flight controller done. And then this coming lecture, we are going to talk about batteries. So I'll see you in a little bit. One second, let me shut this down.